Hi there, my name is Miguel Leon and today's presentation will be about antibiotic resistance and its association with the environment. We will be covering multiple facets on the exploration of antibiotic resistance and ultimately discovering how it is affected by our environment. The presentation will provide a brief introduction on the history of antibiotic resistance, a definition, and other subtopics. We will discuss what environmental factors are influencing and affecting antibiotic resistance today. There will be an analysis of multiple antibiotic-resistant genes surfacing as of late. We will glance at what hazardous microbial exposures are associated with antibiotic resistance. We will take a glance at the evolution of antibiotic-resistant genes within the environment. And lastly, we will study and look into what future outlooks exist in a world of environmental influences alongside antibiotic resistance. We will complete the presentation with a summary of the topics previously discussed and provide you with the references used to gather this information. What is antibiotic resistance? Antibiotic resistance can be defined as microbial pathogens that limit and inhibit the functionality of antibiotic use through mutation, acquisition, and ultimately negatively affecting drug use. The treatment of infectious disease is compromised by the development of antibiotic-resistant strains of microbial pathogens. These pathogens are developed through two primary genetic mechanisms recognized as mutation and acquisition. Antibiotic-resistant genes can enter bacterial populations and ultimately affect communities at a global scale. This development has been classified as one of the best documented cases of contemporary biological evolution. Although a relatively new issue, since use of antibiotic has only existed for approximately half a century, nonetheless has generated key concerns at a global stage. Drug resistance emerges when only an antibiotic or antimicrobial drug and the genetic resistance determinant within the microorganism come together in either an environment or host. There are multiple key points to consider when reading antimicrobial resistance outcome studies. The outcomes are measured by mortality, morbidity, economics, perspective of studies, and comparison groups. There are also factors that improve the quality of research if available. The battle against bacterial drug resistance is an ongoing crisis negatively affecting nations globally today. Case prevalence has been noted to be on the rise and has its accumulation of reflecting the emergence of resistance with epidemic transfer between genes among the bacteria and the epidemic spread of resistant strains witnessed among patients. In order to truly understand the importance of this crisis, one must first be aware of the beneficial factors by the use of antibiotics. Antibiotics have been noted among the few drugs in existence today that not only cure illnesses, that cure illnesses rather than simply reduce the symptoms of disease, and of which many progresses from modern medicine have derived from. It has been stated that this widespread epidemic of bacterial resistance caused by antimicrobial agents may ultimately limit the progress of medicine. Out of the multiple processes that can contribute to the accumulation of bacterial drug resistance, there are three biological processes that are the most alarming. We have new selection, gene epidemics, and strain epidemics. Even with the research and technology available today, demographics of populations under antibiotic stress are little understood because of the information lacking within microbial populations. Biochemical mechanisms of antibiotic resistance and gene determinants vary in accordance to their specific mechanism and possible mutation. Certain examples can be that of aminoglycosides, tetraglycan, rifampicin, amongst other things. These all may have certain mutations varying to their gene acquisition. Antibiotic-resistant gene families and their sources can be sorted by their level of resistance, the producer where they come from, the upkeep, how they are exposed, and the superfamily they belong to. Furthermore, the actions and resistances used by these antibiotics are varied by their class, specific targets, and modes of resistance. Aqueous environments are strongly affected by antibiotics and disinfectants. These measurements are classified by compound, hospital effluent levels, sewage water, surface water, and groundwater affected. These standards of measurement allow to identify the toxicity and resistance that can ultimately arise due to the microbial genes within. Various associations involving both environmental factors and antibiotics have been brought to light as of late, demonstrating plausible relationships. These antibiotics, disinfectants, and bacteria are recognized to be compartmental alongside wastewater, surface water, groundwater, sediments, and soils. The concern encompassing the environment and its negative effects on antibiotic resistance is one of continued growth. Antibiotics are oftentimes released into the environment once their use has been terminated, ultimately being exposed to pathogenic bacteria and increasing the chances of generating a resistance. Even though limited information is accessible regarding these causations and their interrelations, studies demonstrate that these factors are influencing a new wave of antibiotic resistance seen today. Aquatic environments have been noted to be a threshold in the antibiotic resistance community, due to the substances of which enter the system and are not biodegradable. The main processes of substance elimination in the environment are due to bacteria. These resistant genes and bacteria in the environment are viewed as an ecological problem manifesting throughout the globe. It has been noted that the common properties of the environmentally released microorganisms can be further enhanced by improved forms of manipulation. Multiple examples exist, one being the spread of antibiotic-resistant genes and xenobiotic degradation genes due to horizontal gene transfer, coupled to the selective pressures caused by the presence of increasing amounts of these substances in the environment. Genes encoding for the resistance to antibiotics or heavy metals or for the utilization of rare carbon sources are frequently used as selective markers, which is another environmental example of antibiotic resistance. Recombination between E. coli and S. typhimurium is enhanced 1,000-fold when the mismatch repair system is inactivated. Is yet another possible environmental influence affecting antibiotic resistance. The irony behind many of the examples available demonstrating environmental influences within resistance created by these microbacteria is that they ultimately aid in the cleaning up of man-made pollutions attributed today. The first effective use of an antibiotic was in the 1940s by the use of the penicillin. The discovery of the presence of putative bacterial gene sequences in eukaryotic genomes has heightened awareness of the great importance of horizontal gene transfer in genome evolution. The discovery of the presence of putative bacterial gene sequence in eukaryotic genomes has heightened awareness of this evolution. Selection is typically for hostile environments rather than for traits to provide increased studies available. Societal pressures for these antibiotic and disposals have greatly increased within the past few decades. These concepts appear to be of recent trends brought by the evolution witnessed in antibiotic resistance within plasmids and multi-resistant strains. Though various antibiotic-resistant genes are caused by mutation or other functions, most are acquired through horizontal gene transfer originated in environmental microorganisms. After dissemination in the original host, reaching a novel metabolic network is nearly impossible. These natural environments are representatives as a reservoir of these genes. The constant change in these ecosystems existing today is also associated with the emergence of unknown determinants, creating a newly developed bacterial pathogens. Recent studies have shown that contamination of river waters by colonies enriches for plasmid-encoded QNR genes present in waterborne bacteria which facilitate the transfer of these hazardous genes to human pathogens. Also noted is the heavy pollution of metallic substances, which have demonstrated the potential to increase recombination and horizontal gene transfer, resulting in the further dissemination of antibiotic-resistant genes. In often cases, these functions can lead to multiple mechanisms, ultimately creating multi-drug resistance. It is important to remember that many of the antibiotics available today derive from soil microorganisms within nature. With the future in mind, the advancements in antimicrobial resistance is not only causing health disparities worldwide, but is also creating burdens in many economic models currently in existence. There are three approaches that can be used in the evaluation of the economic burdens due to antibiotic resistance within a hospital setting. They can be viewed as overall measures of hospital cost, hospital charges, and resources used due to antibiotic resistance. All antibiotic use, appropriate or not, uses up some of the effectiveness of that antibiotic, diminishing our ability to use it in the future. To avoid further dissemination of previously unrecognized antibiotic-resistant genes into environmental organisms existing today, all bacterial pathogens must be acknowledged. In order to pursue a better future with less antibiotic resistance and environmental hazards, a fundamentally changed view of antibiotic use is needed. An overall rational thought process to maintain these costs sustainable is necessary for an immediate future. These measures should include a continued emphasis on the prevention of the emergence and spread of resistance through antibiotic use and appropriate infection control measures. If the necessary changes are not made, we can see environmental influences continuing to increase within antibiotic resistance and eventually minimizing the capabilities of these drugs widely used. These strategies can not only lower delays in administration of therapy, but can be used to facilitate earlier identification. By decreasing misuse and developing forums that properly address microbial exposures, antibiotic resistance can be eliminated from the future. To conclude, antibiotic resistance has been noted as an ongoing battle that has affected communities at a global scale for more than half a century. It has caused healthcare expenditures to continuously rise within the past few decades and has created serious immunodeficiency caused by antimicrobial resistances, amongst other things. The association recognized by different studies pointing that environmental factors are indeed negatively affecting antibiotic use is alarming. These associations must have light shed upon them, and as these relationships will only continue to grow. Even though minimal information is available regarding these causations and their interrelations, studies must be conducted to further analyze this dilemma. In order to pursue a better future with less antibiotic resistance and environmental hazards, these views must be changed. The societal pressures for antibiotic use and disposal has greatly increased and must be tended to. Though various antibiotic-resistant genes are caused by mutation or other functions, most are acquired through horizontal gene transfer in environmental microorganisms. If the necessary changes are not made in the upcoming future, environmental influences within the medical scope of antibiotic resistance will grow drastically. Politicians, health groups, and elected officials must take the necessary course of actions to avoid such instances to occur. Thank you for your time, and long live science.